It's been a long time since we talked about Unit 1 in depth because we had all of Quarter 2 was Unit 2 and Quarter 3 and a little bit of this quarter was Unit 3. So we need to go back to these concepts from Unit 1. Now again, I think I've said this before, a lot of Unit 1 was Algebra 2 review, which means this content we've seen before and we've been familiar with in other classes before this. We're just going to put everything we need to know from Unit 1 into this little packet here. So this can become a really good resource for you to quickly look at instead of going through all 14 topics of Unit 1. So first thing in Unit 1 is all about graphical behaviors. Now this gets confusing because you have to make sure you know if I'm asking about f or if I'm asking about the rate of change of f. So pay attention to what the question is asking. So looking at f. Is this function increasing or decreasing? Increasing. So graph of f is increasing. Why is it increasing? It's going up. Since it's going up, that means that the rate of change of f is positive because it's going up. Same way a linear function would have a positive rate of change if that line goes up. Same thing for a curve. Its rate of change, the average rate of change in particular, is positive. So next question for you, the graph of f, is it concave up or concave down? Concave up. You can use the shorthand concave up if you want. Please note that if you're writing the words concave up in an FRQ, you do need to write the word out, but these are our notes, so we're fine. This means for us that the rate of change is what? Is the rate of change increasing or decreasing? Increasing. Very good. Okay, so notice the difference in these questions. One of them is asking about the graph, and one of them is asking about the rate of change of the graph. This all combines into a sentence that we're going to need to be able to write for all these. This one is that the graph of f is increasing. I just spelled that word wrong. Please put an E right there. The graph is increasing at an increasing rate. Wow, I'm struggling spelling the word increasing today. I missed the E again. So the graph of f is increasing at an increasing rate, which means it's getting faster and faster as we keep going along this graph. That is going to be a way that we need to describe graphs, and we're actually pretty good at this, so I'm not that worried. For the second graph, for the graph of g, is that one increasing or decreasing? If we were walking on this graph, we would be walking uphill, yeah? That means that the graph is increasing. And since the graph is increasing, what does that mean for my rate of change? Is it positive or negative? Positive. The rate of change is positive. We're still going up. But is the graph of g concave up or concave down? Concave down, which means that the rate of change is what? Decreasing. So the graph of g is blank at a blank rate. What two words should go there? The graph of f is increasing at an, I know it says an, decreasing rate. We can use correct English. At a decreasing rate. So these two graphs are both increasing, but one is increasing at an increasing rate and one is increasing at a decreasing rate. What about the third graph, the graph of h? Increasing, is the graph increasing or decreasing? If I was walking on this graph, I'd be walking downhill. So this graph is decreasing, which means what about the rate of change? Negative. The rate of change is negative. Very good. Same way a linear graph, if you would say the linear graph is decreasing, it's from having a negative slope. Now the graph of h is what? Is this concave up or concave down? Say it with confidence. Concave up. It is concave up, which means that the rate of change is doing what? Increasing. Which seems weird because it's going down, but that rate of change is getting less negative, so it's increasing. So the sentence I write for this one, the graph of h is blank at a blank rate. What do I put there? It is decreasing at an increasing rate. The rate of change is getting bigger because it's going from a super negative slope to a less negative slope. That means the number is increasing. And we have the graph of k. Increasing or decreasing? decreasing, which means the slope is what? Negative. What about concavity? And what does that mean about the rate of change? Decreasing. So my sentence here is the graph of K is decreasing at a, and we'll make this English make sense. Get rid of that and, at a decreasing rate. Your first Gim Kit homework tonight is literally going to be these graphs with all of these sentences, because I need you to be able to look at the graphs. Now, I know that that means you can look at this document and answer all the questions. That's not helpful for learning. Study the document, try the Gim Kit without looking at it. We need to be able to recognize these parts of graphs and this graphical behavior. But we're good at this one, so I'm really not that worried. We just need to get some practice back in. This little exam tip down here, and I know I don't have the highlighters out because we're still in testing mode, but if you have a way to highlight, I want you to highlight this entire sentence down here. Always check to see if the question is asking you about the graph or about the rate of change of the graph. Because we just saw how that answer will change if I'm asking you about the graph or the rate of change of the graph. Knowing what I'm asking is part of the game. Knowing what I'm asking will get you those 2 points on FRQ3. Am I talking about the graph? Am I talking about the rate of change of the graph? That's parts B and C. No, C part I, part 2I on FRQ3. So some more things we talked about back in Unit 1 was called points of inflection. Points of inflection are points where the graph changes from concave up to concave down or vice versa. In calculus next year, you will learn how to analytically or algebraically find these points of inflection. But for our class, since we are pre-calculus, it's going to be very obvious on a graph for us when the graph changes from concave up to concave down. So in this graph right here, the graph has 2 points of inflection. We can see them, they're labeled for you. The graph starts concave what? How does this graph start? Concave down. So we have a concave down section of this graph because it is headed downwards. Then it changes to what? At the point of the inflection, that's when I shift to having a concave up part of my graph. And then exactly where that point is, we can pretty much visually see here, it's going to switch back to being concave down. So the graph switches concavity twice, and those places where it switches concavity is called points of inflection. These are all ways I can ask you or talk about these places where they change from concave up to concave down. Again, we were really good at noticing this, and we have been consistently because I brought this up many, many times, so I'm not all that worried about concavity. We just need to practice it again. On the back here, it talks about average rate of change. Again, we're pretty good at this, so I'm not all that worried. The average rate of change of f over the interval from a to b, which can be written in interval notation or in inequality notation, is given by the formula average rate of change is equal to, and let me hear it because I know you know this one. Minus f of x1 over x2 minus x1. Now, because this definition says a and b, I want you to think of a and b as the x1 and the x2 based on the definition you just said. So you could have also said f of b minus f of a over b minus a, which if we're headed towards calculus gets you closer to the definition of a derivative, so that might be one we want to start memorizing. But this is the same idea. It's fancy slope, bless you. So the rate of change here, just like I said, refers to the slope of the graph at a certain point. For rates of change, just like you did in probably Algebra 1, it's helpful to imagine you are riding a roller coaster along the graph. The steepness of your car is the rate of change. So if we look at this point right here, is this a positive slope or a negative slope? Positive, because I'm increasing. Is it, actually, let me back up. Let me ask a different question. At this point of the roller coaster, what kind of slope do you have? 0. It's a flat line. That's a 0 slope. At the other part of the roller coaster right here, what kind of slope do you have? A negative, because that part of the graph is decreasing. Now, of those 3 points, which one is steepest? The positive one. This is the steepest, so you would have, absolute value-wise, the largest number representing that slope. Because the one that's negative would be less steep. So the absolute value would be not as big as this one. This one would be less no matter what because it's negative. This one would be greater no matter what because it's positive. This one's just 0 because it's flat. Slope of a flat line is 0. Again, this is just kind of fast and furious review. So using tables to understand functions, again, we're really good at understanding which type of function we're using. Maybe the description of it is where we need to focus. So if we look over equal length input value intervals, which is a fancy way to saying making sure the x's go in a particular order. Do you see how this goes 1, 2, 3, 4, 5? It's ordered. They're all one space apart. It could be 2, 4, 6, 8, 10. That's evenly spaced input values. This is how we're going to want to start saying that the x's are evenly spaced, trying to change our vocabulary to over equal length input value intervals. Tuck that away for FRQs. If the differences in the outputs are increasing, that's a word we're writing in. Wow, I cannot spell the word increasing today. If the outputs are increasing, that means that the graph is concave up. If the differences in the outputs are decreasing, that means that the function is concave down. This refers back to the types of slopes we had on the first page. The other thing we talked about when we had functions is looking at the nth degree of a function. So nth degree meaning the second, third, fourth differences of these values. So if we look at the one we have here, how do you go from 1 to 2? Plus 1. How about from 2 to 5? How about from 5 to 10? And then I can tell that this graph is concave up because those values are increasing, but that's not a consistent change, which means this wouldn't be a linear function. That's the first difference. We would check again the second differences. How do you go from 1 to 3? How about 3 to 5? And 5 to 7. Since my second differences are constant, that means this is a quadratic. So to remind ourselves, if the first differences are the same, that's a linear function. If the second differences are the same, that's quadratic. If the third differences are the same, what kind of function is that? Cubic. Very good. What about the fourth differences? Do we remember that name? Quartic, like a quarter, quartic. After that, they don't have fancy names. You just say fifth degree polynomial, sixth degree polynomial, and all of that stuff. But we have to, again, make sure that over equal length input value intervals, we're looking at the x's just to make sure they're in a nice, pretty order. As long as they're ordered in a normal order, we're good. As a little bit extra here, because, again, working on the justifications of FRQs is something that we need to keep in the back of our mind. For a quadratic function, you can talk about the second differences, or you can talk about the average rate of change changing at a constant rate. Not that the rate of change is constant, that's a linear function, but the change in the rate of change is constant. That's what we mean by second differences. The change in the rate of change. If that's all the same number, it's a quadratic because those second differences are the same. The second differences is the change in the average rate of change. Continuing on with our Fast and Furious review. In Unit 1, we then started talking in depth about polynomials. Now, you studied polynomials in Algebra 2, so this was something we should have been familiar with, but I get it. You have a whole summer in between that and this. So when we talk about the zeros of a polynomial, which is topic 1.5, complex zeros, which are the ones that have an I in them, always come in pairs. So if you are told that there is one complex zero, you have to know that the other one exists. So like if you're told x minus 2 plus 4i, it's a complex number, is a zero, you automatically know that its conjugate is a zero. Same real part, opposite sign imaginary part. Multiplicity, and most of you remembered this on our warm-up today. If a factor is repeated a certain number of times, it has a multiplicity of n. And if 0 has an even multiplicity, the graph will bounce off the x-axis at that 0, which is exactly what happened in our warm-up today. They had a bounce on that value, 0 for the 0. Again, we reviewed end behavior in our warm-up, but we'll write down some actual information about it. The leading term, which is the highest degree, determines the end behavior of a polynomial function. It is the strongest or overpowering degreed value in that polynomial. We determine the right side end behavior first. The right side's the easy part. It follows from the leading coefficient. Then you determine the left side end behavior. So right side end behavior, I'm skipping right here because we always do the right side first. Right side end behavior is talking about as x increases without bound. That's going to be part of our vocabulary for FRQ 2. It asks about end behavior. Yeah, 2. For the right side end behavior, if the leading term is positive, okay, leading term is positive, that means the right side value goes up. It goes up to infinity. If the leading term is negative, that means we're going to go down. The leading term controls the right side. Positive goes up, negative goes down. It controls the right side. Leading coefficient controls the right side. Get that in. The left end behavior comes from whether the left side should match or be the opposite. So as x decreases without bound, which is the limit as x goes to negative infinity, we then have to think about the degree of the polynomial. If it is an even degreed polynomial, that means it goes the same direction as the right side. So if the right side went up, left side goes up. If right side went down, left side goes down. If that polynomial or the degree is odd, like straight up an odd number, like 1, 3, 5, 7, the left side has to go opposite. So if the right side went up, left side would go down. If right side went down, left side has to go up. That's end behavior. So let's see a quick example here. Here's a polynomial. We have both the equation and the graph, and we're going to fill in this information. The graph of f has zeros where and where? -1 and 2. We see that there are zeros here and here. So at -1 and 2. One of the questions on the FRQ from the mock exam we gave on Saturday literally asked what was the zero of the graph. A lot of us got it, some of us did not. Don't overthink it. It's just looking at the graph, seeing where it crosses the x-axis. It goes on, this question says, there is a bounce at x equal to what? At x equal to 2, because this term is squared. It has an even multiplicity. So we know it's going to bounce at that 0, which we can visually see on the graph. In fact, let's write that in. These are our notes. This is what a bounce looks like. The leading term of f is -0.5x squared. How did I get that? Because this is not multiplied out, so you can't just see it. But where did the -0.5x squared come from? Let me rephrase. Where did the -0.5 come from? The constant in the front. Where did the x squared come from? Oh, sorry, cubed. This should be cubed. Say again? All of the x's. There's one x here, and there's 2 of them here. So that means there are x cubed terms in my leading coefficient. That means that the leading term is negative, which implies that the right side goes what? Up or down? Down. Negative means goes down because the leading coefficient controls the right side. And that makes sense because we have a picture of this graph. It does go down on the right side. Since the degree is odd, the degree is 3. That's an odd number. Is the left side going to go the same or the opposite direction? Opposite of the right side. So if the right side went down, left side goes up, which again makes sense. We have a picture of this graph. This is what I did on that practice problem in our warm-up today. is I looked at the leading coefficient and the degree so I could think about the end behavior and draw the graph quickly. If we write this as a limit statement, we'll start with the right side because we should start with the right side. The right side went down, so the limit as x approaches infinity is negative infinity. In words, we would say as x increases without bound, x is going to infinity, the graph of f decreases without bound. And I've asked around for other AP teachers, and when I went over the FRQ with you guys last week, I said you only needed the limit statement. I think I was wrong. I think you need all of this on that one question for the FRQ. You'll need it in words and as a limit statement. So this is another one of those sentences we want to start to memorize and changing the values. The left side end behavior we know has to go the opposite direction, which means instead of negative infinity, it goes to infinity. We would write the sentence as x decreases without bound, the graph of x increases without bound. So we'll practice writing those sentences since I believe now you need both the limit statement and the English statement. It's been on everything I've seen. Again, fast and furious. We're getting all of Unit 1 into one little packet. Even functions have symmetry over the y-axis. They can fold over the y-axis like a book. If you plug a number in and you get its opposite, and it's what? If you plug one number in, like 3, and you plug its opposite in, like -3, you should get the same value out of the function. That's what it means for it to be even, because it can fold along the y-axis. An odd function is going to have symmetry over the origin, which for me, I'm going to say this is a spin, which is maybe not the most mathematical language to use, but you put a pin in the origin and spin it, it should land right on top of itself. Visually, it makes sense to me. If you plug in a number and the opposite number, you should get opposite answers. Odd, opposite. Odd, opposite origin. Look, I'll start with O. Odd, opposite origin. Our fast and furious review continues on the next page. Solving polynomial inequalities. This is just, there's nothing to fill out here. These are the steps. It also gives you an example of a sign chart that you could use if you didn't want to use end behavior to try to draw this graph. So you have an example there to look if you need it. This is basically what I did faster with end behavior on the warm-up today. This is how you'd algebraically solve it. Then in the second part of topic Unit 1 was all about rational functions. You did learn about these in Algebra 2, but it was at the end of the year, so you probably all were tired of learning, so we need to maybe slow down on this part. Rational functions are fraction functions, meaning there is a polynomial in the top and a polynomial in the bottom. We have to understand the different scenarios and the behaviors of these graphs when we have polynomial divided by a polynomial. In case number 1, it says n bigger d, so it's trying to tell you that the numerator is bigger than the denominator. When I taught you this, I used the acronym bigger on top. This was Botten. Top heavy, bigger on top. A lot of resources online are going to call it top heavy. We called it Botten, bigger on top. The n stood for the fact that there are no horizontal asymptotes for this graph. So for example, this is a Botten graph. The degree on top is 4. The degree on bottom is 3. Bigger on top, there is no horizontal asymptote. So again, Botten graphs, the top-heavy graphs, do not have a horizontal asymptote. They will, however, have a slant asymptote when it is bigger on top by 1. If you see that it is bigger on top by 1, specifically like this example, it won't have a horizontal asymptote, but it will have a slant asymptote, meaning your end behavior goes to positive or negative infinity. Case number 2 is when they had the same degree. Does anyone remember the acronym that I gave you for when they have the same degree? BETC. That stands for bottom equal to top. The C stands for coefficients. In this example, it will have a horizontal asymptote, and it specifically will have the horizontal asymptote at the fraction -2/5. So again, same degree. Those are our BETC functions. bottom equal to top coefficients. You just snag those coefficients of the biggest number, biggest degree, leading term on top and leading term on bottom, and that creates your horizontal asymptote as well as your end behavior. I already heard somebody say it. Case 3 is when it's bottom heavy. What acronym did I use for bottom heavy? BOBO. Bigger on bottom has a horizontal asymptote and it's 0. So the second O is a 0 if that helps you, BOBO. This is a BOBO graph because you see it's degree 2 on top, degree 4 on bottom. There's no like extra bigger on bottom by 1. If it's bigger on bottom, then that's going to be bottom heavy and the horizontal asymptote will be 0, the end. That means the end behavior will be 0, the end. So I used the acronyms Bobo, Botan, and Betsy. If you go online, look for resources, you may see top heavy, bottom heavy, or same degree. Same thing. Last little bit here before you're done listening to me talk. When it comes to rational functions, this is probably like what I would put a star next to. This is going to be the things that I have seen the most show up in questions in a variety of ways. It asks about the zeros, the holes, and the vertical asymptotes for these graphs. Now, I think last week at one point we had a review question and a warm-up about these, and we actually we remembered, so I'm feeling pretty good. But a function is going to have a 0 when the numerator equals 0, and where the denominator does not equal 0, because that would be a hole. There will be a hole when the denominator equals 0 and cancels out with the numerator. A vertical asymptote will have a denominator equal to 0 and does not cancel out with the numerator. So the way I think about this is what I like to do with these functions is cancel first and see what has completely canceled out of the denominator and what has stayed in the denominator to help me find these different things. So if I look at this example, for me the more functional definition here would be looking at this rational function, it's completely factored. Always factor first. Are there things that are going to cancel out here? Yeah, what's going to cancel out? The x plus 3. Now there are 2 on top and 2 on bottom, but that's cool. They completely cancel. When it completely cancels, does it make a 0, a hole, or a vertical asymptote? A hole. So I'm going to go ahead and put that above this just for myself to think about. Okay. What else will cancel? Ooh, it'll cancel 1 on top and 1 on the bottom. If it remains in the bottom after you cancel, is it a 0, a hole, or a vertical asymptote? It is a vertical asymptote. If it remains in the denominator after canceling, it's a vertical asymptote. So the difference here, the hole completely canceled, top and bottom. Vertical asymptote stayed in the bottom. What else is going to cancel here? X minus 4. How many cancel out of the top? 3. And all of them cancel out of the bottom. Does that make a 0, a hole, or a vertical asymptote? It actually makes a hole. Let's talk about why. In this graph, if we were to rewrite it, would there be an x minus 4 in the denominator at all? No, but you're still not allowed to use that number because if you plugged in 4 to this function, the denominator would become 0 and you broke the graph. So we can't have that happen, which means there's a tiny little hole there for a function. So if something cancels, it is either going to create a hole or a vertical asymptote, which means what's the only factor up here that nothing canceled with? That is your only 0. Nothing, no part of it canceled, not out of the top or bottom. It stayed in the numerator after canceling. That is a 0. If it completely cancels out of the numerator, it's a hole. If it stays in the denominator, it's a vertical asymptote. Which means for this one, the 0 is only at x equal to -5. The holes are at -3 and at 4. And it only has a vertical asymptote at x equal to 1. Notice that all of those signs are the opposite because you set them equal to 0, solve for x, just change signs. The last 2 things on this page I'm not even really going to go over because they're important, but we want to spend our brain power on the main important things, which is going to be the stuff we've already talked about. If I've asked you to find the slant asymptote, that's a Botan graph, bigger on top by 1. You do have to do long division. So here's a nice, cute example of long division. The last thing is about the binomial theorem and Pascal's triangle. Again, important, but maybe one question, so it's there for you to review if you're really shooting for the 5s, but if you're shooting for 3s and 4s, maybe leave this and focus elsewhere. Yes?